So a row space is a subspace of Rn, and where n is the number of columns, and the column space is a subspace of Rm, where m is the number of rows. So it's another one of those things that look like it's written backwards. But let's see why this makes sense. Let's see if this makes sense. I hope it makes sense. And let's do this by looking at an example. So here's our example. We have a nice simple matrix. It's small, and the possible spaces or subspaces are from R2 or R3, which is something we can visualize and something that we just discussed last time. So let's see. Let's first take a look at the size of A. A is a what by what matrix? Is a 2 by 3 matrix, and that's 2 rows and 3 columns. Okay, and so let's take a look at the row space. So the row space tells us to take the rows of this, rows of A. And how many rows? We have 2 rows, so we have 2 vectors that we can look at. Does it matter if I write the vectors vertically or horizontally, or does it matter? We are all flexible by now, right? So I'm going to write it as a vector with commas, like a point. So there's only 2 rows, so I can list them down. And here are my 2 rows. So the row space is a span of these 2 rows. I have a question. Is this are these 2 vectors linearly independent? So by inspection, you should be able to tell by inspection if 2 vectors are linearly independent, right? Like, can I multiply one of these vectors to make it look like the other one? No, I can't do that. So they're linearly independent. So the rows of A are linearly independent. So from last time, we said that if we have 2 linearly independent vectors in R3, I'm going to attempt to draw this in 3 dimensions. It's a very poor attempt. But I have 2 vectors in R3, and what do these 2 vectors span in R3? They would span a plane, right? So if you imagine connecting these 2 vectors and just having it extend out, maybe the plane doesn't look quite like that, but let's say it looks like that, and so it spans a plane. And the plane goes through the origin. So this looks like it is a subspace in R3. Right? So I have 2 vectors in R3. This is a plane through the origin, so I have a 2-dimensional subspace in R3. So the span, you can look at this, a row of A, more formally, that's how we denote this subspace, is equal to the span. Do you use curly braces or parentheses for span? Doesn't really matter. I'm going to use parentheses. I kind of had a half curly brace, half parentheses there. And I'm going to switch over to a vertical vector so I can save some row space. Get it? No. Save some space. So the span of this is a 2-dimensional plane in R3. Okay? So there's that thing that this is a row space. Should be a subspace of Rn. N is the number of columns. We're looking at rows, but then we're counting the columns. But if you look at the columns, they're exactly the size of those vectors. So that makes sense now, right? Yeah. Each row has 3 components, and the components are counted by counting the columns. And so that tells you the space that you live in, your big vector space. And then depending on how many you have, you could possibly have a 1 or a 2 or a 0 or 1 or a 2 or a 3-dimensional, or in this, yeah, in R3 you can have a 3-dimensional subspace. So in this case, our subspace is just 2-dimensional, which is a plane. All right. Now in contrast, when we look at the column space, we have to look at the columns. And this one I'll write vertical again, 1, 1, 0, 1, minus 1, 1. All right, let's think about this. All these vectors have 2 components, so we must be talking about this being a subspace in R2. What are the possible subspaces in R2? Either just a point, a line passing through the origin, or all of R2. Okay? So they are either 0-dimensional, 1-dimensional, or 2-dimensional. I have 3 vectors here. Do you think this will be a 3-dimensional subspace of R2? No. There's no way this could be a 3-dimensional subspace, because in R2, I can have at most 2 dimensions. I can't have anything 3-dimensional if I'm living in R2. So, given that I live in R2, I have to be only a 2-dimensional, at most 2-dimensional, possibly 1-dimensional subspace. Which means that these 3 vectors should be linearly dependent. Okay, I don't know if you can eyeball it, but I can't. So, well, can I? No. So what we're going to do is, are at least 2 of these independent by inspection? Can we see if 2 of these are independent? Or are they all dependent? Like if I pick 2 at a time, is it all dependent? Do you understand my question? No. If I just focus on these 2 vectors, can you look at them and say they're independent or they're dependent? So just by looking, by inspection, you can say they're independent. Yeah, that's a big thing. Is 0 makes it easy. It doesn't necessarily just have to be 0. It could be some other number. But the idea is that can I multiply 1, 1 by something to make it look like 0, 1? And there's no way to do that. Okay, so they're independent. So I have 2 independent vectors. In R2, and if I just look at the span of those 2 vectors, what am I going to get? All of R2. So a column space of A is a span. Now I'm going to write this down. This might look kind of weird, but I'm going to write down the span of these 3 vectors But since those three vectors put together are linearly dependent, I can essentially eliminate one of them and just take two independent vectors. And since there are two linearly independent vectors in R2, this is exactly, I don't have to put all of here, but I wanted to stress the idea this is everything in R2. Okay? Yes? If two vectors are independent, and the other, well, there's only one other one here. What do you mean? For this particular problem? Or in general? Yeah, if two vectors are linearly independent, and then you see that another two vectors look like they depend on the other two vectors, then we can just eliminate those. Yeah? Yes, when you say span. Now, the idea of just collecting the smallest amount of vectors that would span the same thing and making sure that all these vectors are linearly independent, that comes in a little bit later, so that's we're kind of prepping for that. But the span of this is the same as the span of this. And so what we're saying is that if let's see, yeah, let's get that visual for R2 here. So this vector 1, 1, and there's a vector 0, 1, and then now there's a third vector, negative 1, 1. I can really just erase one of those vectors and I would still span everything. So decided to just erase the last one. I could have taken the actually no, if I take is that right? Negative 1, positive 1. Oh, that last vector is not correct. Negative 1, positive 1 is up here. So if I erase any of those vectors, any of the two vectors that are left would still be linearly independent, and so they would still span all of R2. And if the idea of span still isn't making sense, remember that I made an extra video on linear combinations and spans. I think that's a good video to try to get these things under control. All right. So we just did this by inspection because we knew some information about R2 and R3. But if this thing were to go at a higher level, then we can't rely on just our intuition necessarily, unless you really have good intuition. Can't rely on that, so we need some mechanics on trying to figure out how to actually do these problems, or how to find the row space and the column space. And to find a row space and column space, what we're interested in is to really pare down, just slim down the number of vectors. If they're linearly dependent, we want to just trim them down to just as many vectors as what's needed. So here's a more formal way of finding the row space and the column space. We don't say find the row space and the column space. We actually say finding a basis or representative for the row space and the column space, so that we can describe it. So here's how we would do it more formally. And for this one, it's easy enough to do because what we're going to do is we're going to row reduce. So when we row reduce, it looks like I'm going to take row 1, multiply by negative 1, and add it to row 2, replace row 2. So just a simple row operation like that would give me 0, 1, 2. Okay? So that's only one step, but once you reduce it like that, you have your reduced. It's not a reduced row echelon, it's just regular row echelon form. So the row space is spanned by however many non-zero rows you have. Now, none of the rows turn to 0 in this example, but we could just say it's the same thing. So spanned by the non-zero rows. And it turns out that we can use the original set, 1, 0, negative 1, 1, 1, 1, or we can actually use this other set, 1, 0, negative 1, and instead of 1, 1, 1, we'll use 0, 1, 2. So it looks like the span of these two vectors up here is the same as the span of these two vectors. Now we can visualize this because I could take out my graphing calculator program and I'll draw these vectors, and we'll see that all these vectors will all be on the same plane. We'll take a look at that in a minute. But let's talk about the column space. Column space is spanned by and what we do for the column space is we look at the pivot rows, or the rows with non-zero elements as a leading. I circled those two, but I actually didn't want to circle those two. What I wanted to circle was the two columns from the original matrix that match with the columns of the reduced matrix. So the two columns in the original matrix would be the columns that we're looking for, 1, 1, 0, 1. Okay. We'll get a better example with a larger matrix to deal with this stuff. But I do want to take advantage of the fact that this is an R2 and R3. And let's take a look at, to show that the row space of A up here being the original rows versus the row space over here being the reduced rows should be the same. So I'm going to take out my graphing calculator and graph a couple of vectors. So these two vectors over here, they're drawn in purple. These two vectors span a plane in R3. Right? Now what we're saying is that if I compare that with this other vector, 0, 1, 2, it should be on the same plane. Let's see if it actually turns out to be on the same plane. So if you look at it carefully, I'm going to stop it at the right moment where they look like they're all on the same plane. Right here, you can see that they all would be lying on the same plane. So that means that the span of these two vectors after the matrix has been reduced, the span of those two rows is the same as the span of the original two rows. Okay? And that is, the span is exactly the row space. So let's do another example in a higher dimension where we are going to try to identify the row space. 19 or 20. Let's do 19. So 19 is a 3 by 4 matrix, which means the row space should be in R4 and the column space should be in R3. So A is a 3 by 4 matrix. So the row space should be a subspace. I'm going to use this symbol for a subspace. It's like a sideways U, smooth gray. Let's just actually write it out. Is a subspace of R what? 3 or 4? 4. So remember, for the dimension, or for the vector space for the row space depends on the columns, number of columns. Because each row has 4 components, right? So the column space of A is a subspace of R3 because those columns are 3-dimensional. All right, so let's go through the row reducing process. Oh, good. So this looks like the first step is already done. I just have to do one more step. So the first row doesn't change. Second row looks like it's good. And so I need to take the second row, multiply that by -1, add it to the third row, and then replace the third row. So 0, that makes this 0, and then multiply by -1. That makes this into a 0 as well, and this is not 0 anymore. That's -2. Okay? So how many non-zero rows do we have? We have 1, 2, 3 non-zero rows. So our row space is going to be 3-dimensional. Our row space is going to be a 3-dimensional space in R4. So we can say row of A is going to equal to the span of, now I need 3 vectors. I can use the original 3 vectors up on top, or I can use this reduced vectors, the rows. So 1, 0, 0, 1, 1, 0. Whoops, sorry, I'm doing that wrong. That's 1, 1, 0, 1, 0, 1, -1, 1, 0, 0, 0, -2. So in this 4-dimensional world that we can't visualize, we have 3 vectors that span something in 4D, that span a 3-dimensional space in 4 dimensions, and that is our row space. So there's 3 vectors here that are linearly independent. So it looks like it's this is a 3-dimensional space in R4. Okay, now the column space. So here's where you can identify the column space. You want to look at, maybe I shouldn't circle the whole thing. You want to look at the leading terms for each row, right? So that's the first, the second one, and then the last one. And so you're looking at the first column, the second column, and the last column. And what you would like to do is you'd like to gather the first column, the second column, and then the last column. And that is going to be your column space that is now a list of linearly independent vectors. So your span, technically your span is the whole thing, but the whole thing is linearly dependent. And so what you want to do is you want to eliminate things that are not dependent, and so we can eliminate that third column. And so the span of 1, 0, 0, 1, 1, 1, and 1, 1, negative 1, the span of these three vectors is your column space. So you have, this is from R3, you have three vectors that are linearly independent in R3, so what can you say about the column space? All of R3. Because there's three of them that are linearly independent, so it has to be a three-dimensional space. So this is all of R3. Okay. So is that clear, how to find the row space and column space? Finding the column space is tricky, so that's really the only thing. And for the row space, I decided to choose this that's reduced, but I could have chosen the original rows as well, and they would be the same thing. So in fact, that's a theorem that's going to be coming up right now. Right now. So as long as you have two row equivalent matrices, the rows of A and the rows of B span the same thing. So it might not look exactly what we've been talking about, but it is saying the same thing. This theorem 3.20. So what this theorem says is that it allows us to either take the rows of the original matrix or the rows of the reduced matrix, non-zero rows. Okay, if you're able to get one of them to be 0, then you don't take that from either matrix. Yeah. This is only for rows, right? Columns is different. Because when you do the rows, when you do the row reducing, then it keeps it row equivalent. And so you're still dealing with the rows, but who knows what happens to the columns when you do that, so you can't. This is only for the rows. So you could take span of the non-zero rows of the reduced matrix. And by taking the non-zero rows of the reduced matrix, you're essentially guaranteeing that those row vectors are linearly independent. Okay? And I keep wanting to stress the idea of collecting independent vectors, because that is how we're going to build our dimension and stuff like that. All right, another theorem. If you have an m by n matrix, oh, I should do this on another page. If you have an m by n matrix, we've done these systems where we set it equal to 0 and we solve for them, right? So it turns out that the solution set is also a subspace of Rn. Let's see if this makes sense. Let's go back to our example. And let's solve this matrix with AX is equal to 0. Let's set up a system of a homogeneous system of different, or I didn't mean to say differential equations. A homogeneous linear system, and homogeneous just means it's set equal to 0. And then let's see if we can solve for this. So an AX is equal to 0 would look like this. You have an x, AX equal to 0, and that's a 0 vector. Just let's make sure we got the dimensions of x correct here. So A is this matrix. And I want to make sure the sizes work here. So if we look at these vectors as like row or column matrices, we actually have to look at them as a column matrix. And we do the matrix multiplication, it's going to be column times row, right? So how many variables do I need here for my x for this thing to work out? 4 variables, right? So let's start with W. W, X, Y, Z. So I need this to be a 4 vector. And then the 0 is a 0 vector. And how many elements do I have in the 0 vector? How many? Like if I do column, row, and then I get a number. Column, row, and then I get a number. Column, row, and then I get a third number. So my 0 vector should be a vector with zeros in it. And how many components does it have? It should have 3 components. Okay? So the solutions to this have to be, this is a 3 by 4 matrix. It has to be from R4. Right? So solutions are in R4 because you're looking at these 4 vectors. So let's yeah. It would still be a subspace of R4, but it would be 1 dimension less than you would expect. Your solution it will be 2 by, no, not necessarily. It would still be a 3 by 3 matrix, and it'll just, something weird will come up. I'll see if I can come up with an example that does that. So anyways, let's do this right now. We know how to solve for this, right? I think. Do you remember? We write it as an augmented matrix: 1, 1, 0, 1, 0, 1, negative 1, 1, 0, 1, negative 1, negative 1. Augment with the right-hand side. And it's only 3 zeros. And then you row reduce, right? And when we row reduce this, we did this already. So 1, 1, 0, 1. And the right-hand side looks like it's always going to be 0. 0, 1, negative 1, 1, and then we got this to be 0, 0, 0, negative 2, 0, something like that, right? So if we have, in this example, we have a problem, not a problem, but we have, we're trying to solve for these things, for w, x, y, z. So let's see if we can solve for this. Let's see. So z is the last variable. So it looks like negative 2z is equal to 0, which means z is equal to 0. And now we have a free variable. So we have a free variable because we have that extra space here. So let's call what's the one before the z? The y is a free variable. And so we have z is equal to 0. We'll set y equal to t. And so let's continue solving for this. Our second row here gives us an x minus y plus z is equal to 0. Well, we said z was equal to 0 and y was equal to t. And so what's x equal to? X equals to positive t. Right? And then our first variable is w. So from here, I have w plus x plus 0y plus z is equal to 0. So w is equal to, z is equal to 0. And x, we found that to be t. So you bring the x on the other side, that's negative x, so it's negative t. So what is our solution? Solution for ax is equal to 0. Our solution is going to be a w, x, y, z vector. So vector, well, it's a set of vectors that satisfies this equation. It's w is equal to t times negative 1, x is equal to t times 1, y is equal to t, and z is equal to 0. So whether you're in 2 or 3, or in this case 4 dimensions, what is this thing here that we're looking at? What is this? This is a what? No. Since there's only one parameter, it only goes in the direction of that vector. And the t is a parameter. So this is a line in R4. How many dimensions is a line? A line is 1 dimension. Where did that 1 come from? Oh, let's see. Okay, so this is a line, and it goes through the origin, right? Because there's no other point here, so when t is equal to 0, this is 0, 0, 0, 0. This is a line that goes through the origin in R4. So, and you can think about this is, the other way you can think about this is a one-dimensional subspace that's spanned by this negative 1, 1, 1, or negative 1, 1, 1, 0 vector. So n, in this case, is a subspace of R4, and n is equal to the span of this one vector, negative 1, 1, 1, 0. And it's one-dimensional. Probably should change colors of pens here somewhere. It's all green now. Okay? So they call it n for a reason. Anybody know what this term is called in linear algebra? What? No. What did you say? Nothing. Oh, nothing. I thought you said it. What? Null. Where am I? N is a null space. So the null space of a matrix is going to be all the vectors that live in Rn, where n is the number of columns, are all those vectors that make the matrix go to 0. Okay? It makes the matrix go to 0. In fact, we can mess around and try some... Whoa, no, stop. In fact, we could take this, we could take the matrix that we were working with, and that vector that's supposed to be in the null space, oh man, come on. Multiply this by anything, because the null space is supposed to be the span of this vector. Multiply this by anything. Give me a number. 6. So if I take this, sorry, getting too excited. So if I take this vector minus 6, positive 6, positive 6, 0, and I perform this multiplication, this should take me to 0, because this x over here, this vector, is some vector in the null space. And when I take any of those vectors from the null space and multiply it with a matrix, I should get 0. So let's do this. This is 6. Negative 6 plus 6 plus 0 plus 0 is 0, so it's negative 6 minus 6. Next one is 0, 6, negative 6, and 0. And then the next one is 0, blah, 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 0. Okay, so that's what it means to be in a null space. And so the span of this thing means that any scalar multiple of this vector should send this matrix to 0. And that's exactly what's happening. Okay? So that's a null space. It would have been more interesting if our null space was not just one-dimensional, but if it was two-dimensional, three-dimensional, or something like that. But it's the same idea. All right. Now, I don't know what this is doing here. Matrix A whose entries are real numbers. Yeah. That might be important. But I want to talk about the basis. This is where we're leading towards. A basis of a subspace is a set of all vectors that spans this and that are linearly independent. So that's what I've been trying to do, trying to get at. If we have 4 vectors that are linearly dependent, well, what I'd like to do is I'd like to take away some of those vectors that make it dependent so that I have just a set that's linearly independent. Okay? And what this is going to help us do is it's going to help us find the dimension. So to find the basis, you take all your vectors, whatever vectors that you have in your collection, you row reduce it, you put it in the matrix and you row reduce it. And then you collect all the non-zero remaining rows to form the basis of whatever vector it is you're looking for. Now, if you have an actual matrix, so this is exactly what we did in our example. We reduced the matrix to use the row echelon reducing, and then we looked at all the non-zero vectors, and we collected that, and we said that formed the basis. We looked at the columns with the leading pivot column, that's a non-zero pivot column, when we collected those, and we found a basis for the column vector. And then what you could do is you can augment the zeros, and then you're going to get the basis for the null space, which is what we did. So these steps over here are steps that we already took as our example for that A. We actually found a basis for the row vector, for the row space. We found a basis for the column space, and then we found a basis for the null space. Just to show you again, by row reducing this, we found a basis for the row space, 3-dimensional. We found a basis for the column space, 3-dimensional. And then when we took that and we augmented it with 0, we found a basis for the null space. So those 3 spaces associated with a matrix are going to be important for us. Okay? And then there's one more formula that's super important that we'll talk about on Monday that relates the basis, the dimensions of the null space, the row space, and the column space. All right. We're packing up a little early today, huh?